Cool. Okay. So I'm going to talk about information, compression, and learning, and basically maybe a few life stories and how I got through them. And so maybe we can, if we're talking about life and maybe growing, maybe we can kind of liken it to an apple tree. Starts very small and very compressed, and yes, even though it's very compressed, it contains a lot of information. And then when you observe that there's much there, and then when it starts growing, you can start getting a feel to what's about to happen, and you say, oh wow, I see, okay, I'll get more of this green stuff here, more of this brown stuff here, and we'll keep growing. And then maybe you get a broader view and you see, oh, there's not just one tree, but there's a whole bunch of them, and they have some structure that maybe could be exploited. And one of the main things that we know about exploiting is you say, okay, maybe I'm not so interested in the whole tree, but I'm actually interested in some specific aspects of this tree that I can eat. Okay, and then once you and the tree get older, then some of the apples maybe start getting rotten, and maybe you're starting to compare them to oranges that your neighbor has, and so on. So there are some extensions that you could look at. So we're going to go through this path with the small exception that this talk really, one thing that it's missing is compression. So the talk itself is probably like 2 hours long. So we'll just go and see how far we get in 1 hour till Paul shows me this sign, and then we'll stop. So we may not get to everything, but hopefully we'll get to a fair bit of this information. And as we go along, maybe just keep in mind a couple of things, a couple of life lessons. So we all know that if someone gave us a lever, then we could move the world. But I think as information theorists, we found out that if someone gives us a measure, then we can learn the world. So we'll see some examples of that. And we also know that it takes a village to do almost anything. And in particular, we will take a scientific village to develop a theory. So much of what I'll talk about is not our work, but maybe other people's work. Okay, cool. And maybe last but not least, very important, that when you do this work, then not always you get the beautiful results that you like. Sometimes you cannot get the results. Sometimes you find out that other people got the results before you, or the results you want to get cannot be achieved. So it looks really bad, but if you just make a small change, then maybe it becomes really rad. So keep that in mind when things are bad. Maybe they'll be better. Hopefully we'll see some of that in this talk. Cool. Okay, so we're going to start with compression. And of course, compression, the way we talk about it, started by Claude Shannon. And Claude Shannon did not just come up with a measure to learn the world. He came up with a measure that actually changed the world. And let's discuss what it is. So he said, okay, you have a known distribution P over some discrete supports at X, and you have a random variable that's distributed according to this distribution. And what you want to do is you want to encode the value of the random variable. So you want to map every value to a sequence of bits, and maybe we said that we map X to LX. So let LX be the number of bits that you use X to encode X. So from the little bit we know about Shannon, he was really interested in games. And you want to minimize the expected code length, which is summation of P of X times L of X. Now, Shannon probably was thinking about a game when he had it. So he was thinking, okay, you have a game, you have home team and the guest or visitor team. So there'll be an outcome. So the outcome could be either the home team wins or the visitors win, or there's a draw, and maybe these are the probabilities. So the home team wins with probability quarter, the visitors win with probability quarter as well, and it's a draw with probability 1/2, let's say. So then if you want to encode them as bits, then one reasonable thing to do, which most people would probably do, is if the home team wins, you encode it as 0-0. If the visitors win, you encode it as 0-1. And if it's a draw, you encode it as 1. And you notice that so the number of bits that you use When the home team wins, it's 2. When the visitors win, it's also 2, 0, 1. And it's draw, it's a 1. And you'll notice that as the probability increases, you want the number of bits that you use to decrease, because you're going to use this value more times. It happens probably half. So you want to use fewer bits in that case, okay? And you can, in fact, see right here the optimal code length. You'll see that the length that you assign to every outcome, possible outcome, is just the log to the base 2 of one of its probabilities. So, for example, the home team means probability a quarter. So you'll assign to it length of log 4. 1 over p is 4. Log 4 to the base 2, which is 2. The visitors win, again, with probability quarter. So you assign to them as well log 4, which is 2. And it's a draw with probability 1/2. So you assign a code length, which is length log 2, which is 1. Okay, that turns out to be optimal. Okay, and so if we go back to the compression, then what we saw is that you want to map x into log of 1 over p of x bits. Okay, and therefore the expected length is going to be just the summation, the expectation of log of 1 over p of x. So it's summation of the probability of x times log of 1 over its probability. Okay, and that has a name. It's called entropy. And that is really the measure that Shannon came up with that in many ways changed the world. So it's one simple measure that had important implications. Okay, cool. So, so this is compression. And there's a very important limitation with this scheme, and what is it? So maybe we can look at some clues. So maybe we can look at English words, or if you maybe you want to compress some text, or there's a genes, you want to compress that sequence of genes, or you're an ecologist, you want to compress what you have seen. And what is the problem? That in order to find the optimal distribution, we had to assign code length, which is log of 1 over the probability, but in fact, nobody tells us what is the probability. So in any application in life, nobody tells what's the probability of any word, on any word, any gene, and so on. So we need to kind of learn them. Okay, so P is unknown, and the question is, how do you construct a code? Okay, so this looks bad, right? Because we don't know how to do it, but in fact, it opens it really opens the world to a whole bunch of new things. Okay, so let's talk about universal compression. So that started by a few people, and maybe one of them the people attribute to is Rissanen. And so we have seen the coding an equivalence between coding and probability. Okay, so if you have a distribution, then as we saw, it gives you an encoding where you assign the length, which is log of 1 over p. The opposite is also true. If someone gives you a code length, then you can assign to every x a probability, which is 2 to the minus lx. I just invert this formula. So p of x, the probability is going to be 2 to the minus lx. Okay, so that's, if you have a code length, that means that you have an estimate, you have some estimate q about the distribution. So really there's a one-to-one mapping between distribution and encoding, okay? And that leads us to KL divergence. So we have P, which is unknown, and you want to find a good code for P, which is not known, but every code will be equivalent to some distribution Q, right? If you give me a code, I just have 2 to the minus lx, that's your estimation of the distribution. So it will be equivalent to some assumed distribution Q, and the expected length is going to be summation over P of x times log of 1 over the probability that you assign, okay? And the added number of bits over the entropy is just the expected length that you'll use, summation P of x log 1 over Q of x, Q is your estimate, is your guess about the distribution, minus the entropy, minus summation P log 1 over P, and that's just summation of P log P over Q. That difference is very important, of course. It has a name. It's denoted by D of P and Q, and it's called the KL divergence. It's maybe like the main information theoretic distance. It means by how much, if you're going to approximate P by distribution Q, how much are you off from the entropy? How much more bits are you paying? Okay, so it's the extra number of bits above the entropy when you encode X, which has distribution P, according to another distribution Q. Okay, cool. And so we know that things get better when you have company. I'm not talking about the company that some of the people here in the front had, but just other friends. that definitely get better both ways. And so instead of just encoding a single value of x, we often want to encode a sequence of observations like speech, or movie, and so on, or even bits, because you can look at a sequence of bits in 2 dimensions. So the simplest assumption is that you have IID, independent samples, according to the distribution P, and we'll denote the sequence by xn. And it's distributed because IID is distributed according to the product distribution Pn, okay? And it's easy to see that the entropy of the sequence, of the whole sequence, xn, is because they're independent, is n times the entropy of x times the individual entropy. So, in other words, it goes linearly with the number of observations that you have. And the minimum number of bits that you need is therefore the entropy of the whole sequence, which is n times h of x, okay? And grows linearly with n, with the number of observations that you're trying to encode. And what is the redundancy? The redundancy is this extra number of bits over nh that you need to describe xn when p is unknown. And it's denoted by Rn, where k is the alphabet size. So as we said, you're going to assume some distribution q over the sequence, and we'll let k be the alphabet size. And so dpq, the distance between the actual distribution and your estimated distribution, is the loss. And now what we're going to do is we're going to do what's common in game theory. We don't know what's the underlying distribution, P. So how do we measure how well we're doing? So we're going to say we're going to be conservative and say, suppose the distribution that's out there is worst for us. We're going to look at the worst distribution. And then what we'll do is we'll take the best estimator. So basically, we're choosing the best estimator that will be good for any possible underlying distribution. So it's called the min-max formulation. This is the standard formulation that people have when you make a decision, nature makes a decision, you see how bad or well you do, so you say, I'm going to make the best decision that I can for any possible decision that nature makes. So I'm going to fix my estimator, and then I'm going to look at the worst possible decision by nature, the worst P, and I'm going to choose the estimator, my estimator, to be the one that minimizes this worst case. So this is called the redundancy with n samples when the alphabet size is k, okay? So it's very easy to see that this redundancy is at most log n. So I'm trying to compress, let's say bits, that's R2. The redundancy, the extra number of bits I'll need, is at most log n. And that is because what I can do is I can describe, I have a sequence xn, 0, 1, 0, 1. I can first describe the number of ones in the sequence, okay? And that will take me log n bits, because I have the number of bits is somewhere between 0 and n, so log n or log n plus 1. And then once I describe the number of bits, I can describe the sequence given that number of bits. Okay. Now notice that if I told you how many bits there are in the sequence, that's better than telling you the distribution, because it's not just I told you that the probability of 1 is a half, I told you exactly how many ones I got. So that's better than telling you what the distribution is. So therefore, the number of bits that you need to describe the sequence, given the number of 1, is at most the entropy. Okay? And to describe the number of ones, you need at most log n. So that means that we wasted at most log n. So it shows that the redundancy with n bits is at most log n bits, but in fact, you can calculate it exactly, and it's going to be roughly 1/2 log n. And with this dot, what I mean is that the ratio between the right and left goes to 1. So it's half log n, and half is the right constant. So getting to log n, redundancy, which is to compressing the sequence with log n more bits than the entropy, is easy. We just describe it, just say how many ones, and then describe which sequence it is with this many ones. But if you do it optimally, then you'll just have half log n is your redundancy. Okay? And when we move from binary alphabet to a larger alphabet k, then the redundancy you can show is going to be k minus 1 over 2 times log n. So when k is 1, it's half log n. But when you want to compress sequences over k symbols, it's going to be roughly k over 2 log n, k minus 1 over 2 times log n. Again, that's the right constant. And the nice thing about it is that it's logarithmic in the number of samples that you get, logarithmic in n. But remember that the compression was n times the entropy. The compression length is linear in n. So that shows that the extra number of bits that you need to compress the sequence when p is not known is negligible compared to the best possible. Okay? And in that case, we said that the sequence is universally compressible, so we said that ID sequences are universally compressible. I can compress them without knowing the distribution in advance. I don't need to know the distribution, I can just compress it. Okay? So you can compress roughly optimally, and roughly means just with a negligible extra number of bits without knowing the distribution. Okay? And then I described it for ID, but there are extensions to Markov chains, to stationary processes, and more. Okay, so we see that something bad turned into something good. You can actually do that. Okay, and there are further opportunities here. So there are a couple of things that are still missing. So first of all, the result that we have was asymptotic. We said this is the number of bits as n goes to infinity. K minus 1 over 2 times log n. That's number one. Number two, we saw that the redundancy was k minus 1 over 2 times log n. And notice that in many applications, k, the alphabet size, is large. Like if you want to compress English, k is the number of words, which is maybe 500,000. You want to compress like DNA sequences. Again, if you look at genes, if you look at products and so on, k is very large. And as k increases, the redundancy is going to go to infinity. So it's only good if what we've discussed so far is only good if you fix the alphabet size and let n go into infinity, like arbitrarily larger than the alphabet size. Okay, so that's another thing. And the third opportunity that we have is that what we saw is how to compress to the entropy, but can we apply this to learning distributions? Okay, right. Okay, so and how do we formalize that? Okay, so that's what we're going to do next, and leads us to estimation. Okay, so distribution estimation. So we want to estimate a distribution from its sample. We want to relate that problem to the compression problem that we just went over. So so you want to estimate this distribution from its sample. So we suppose that, so what we're going to say is that if we have H, we assign the probability that we assign to H, we denote it by Q. P is the actual distribution, Q is our estimate. So if we have, I'm missing here, if we got HH tails, there should be someplace here. Yeah, right. So if we got H tails heads, then our estimate for the probability of H is going to be 2/3. And our estimate for the probability, for example, if we use what's called empirical estimate, is just going to be 1 out of 3, which is 1/3. So an estimator, therefore, is a mapping that takes a sequence of n symbols and maps it to a distribution over the alphabet. Okay, so maps an observation to a distribution. And Qn of x is the estimate of p when you observe xn. Okay, so an estimator just takes a sequence like HTH and maps it to a distribution. And we let, if we observe xn, Qxn is our estimate when we observe the sequence xn. Okay, so what is the estimation loss? So we'll denote it by R. It's going to be, again, we're going to find it the same way. So we're going to look at the expected KL divergence between the estimator, between the probability underlying distribution P and our estimator Q. Okay, and looking at the expectation, and again, we're looking at the worst distribution, and we're going, that's what nature is going to do, find for us the worst distribution. We're going to find, we'll go find the estimator that will do the best for this worst distribution. Okay. Okay, and so it's the least expected KL divergence for the worst distribution. Okay, and so far what we've done with the compression was we said we want to compress a long block, so we look at the KL divergence for the whole block. But in reality, we're given a number of symbols. We want to learn the distribution. We want to see how well we're going to do for learning the distribution over the symbols. So I'm not trying to compress a whole sequence. I'm taking n samples, and I'm trying to find the distribution. Or in other words, I'm trying to find the KL divergence for the n plus first symbol, which is ID. So it's going to be just the regular distribution between the KL divergence between the actual distribution and my estimate. Okay, that's what we want to do now. Okay, so it's the compression loss for a single. You can view it as the compression loss for a single symbol. Okay, and we're interested in the rate in which we can learn distributions over k elements. Okay, so this is one of the cases where we need to appeal to our scientific village. And turns out, so I would say that in information theory was very interested in the compression results, and they got a lot of results about compression, but they didn't quite relate it to this distribution estimation problem, which I think some people have done, and we have done, or at least some people looked at this other problem, as we're going to say now, and what I'm going to do now is actually try to relate these two a little bit. Okay, so back in 2004, these two people, Brace and Sawyer, they considered, so in information theory, there's a bunch of estimators called beta estimator, which you take the number of counts that you have. For example, if you've seen the letter A appear 5 times, you add some beta to it. So you say you've seen it 5.5, and then you just normalize. So they showed that these estimators were suboptimal, and that if you use more optimal estimator, then for any k, you can get this KL divergence to be k minus 1 over 2n. So for any alphabet size k, if you have n samples, you can get the KL divergence from your estimate to the actual distribution. You can get it to be k minus 1 over 2n. Okay, and this is using natural log. Okay, and if the name Brace looks familiar to you, it's because he's quite well known for the Brace paradox. We showed that you can get a road system, like here. You have a road from this point here, 2 roads that lead from the start point to the end point, like the top one and the bottom one. And then if you add one more road here between A and B, actually it will increase the congestion. So even though you added more roads, the congestion will increase. And people actually found out that it holds, including in New York City, and so on. So maybe just shows you that people with good taste work on nice problems. Okay, so they show this, that your loss in estimating the distribution is k minus 1 over 2n, but still is good news. So it looks bad, but it's so actually we looked at this problem, then we realized that they solved it. But still was not bad news in the end, was good news, because first it allowed us to get a simple relation between estimation and compression, which we'll go over soon, and then to look at other distances that they have not looked at, and also see what happens when the alphabets are large. Okay, so the estimation compression inequality. So capital R, remember, is our loss when compressing whole sequence of length n, or the extra number of bits. And we said that was going to be k minus 1 over 2 times ln n. That's an information theoretic result from a long time ago. And you can easily show that it's less than or equal to summation of Ri, because these are like your instantaneous loss. If you use this estimate at any time you're going to use that many bits, that's the KL divergence. And so the total loss is going to be the most sum of those. And if you use the Brace and Sawyer result, that's going to be summation of k minus 1 over 2i. Okay, that's what they showed. And this sum is just k minus 1 just comes out. Actually, k minus 1 over 2, and summation of 1 over I is the harmonic sum is log n. So what that shows you is that actually you can get the sequence compression from individual compression. So you can achieve the compression by point-wise estimation. In other words, and you even get the same constant. So you can think short-term, just estimate well at any given time, and succeed in the long term. Okay, so that's an implication of the result they had. Okay, and it might seem obvious to you, but in fact, I wrote here weight, but we probably will not get there. But in fact, if you look at a little more complex situation, that's not going to be the case, that you can do things sequentially and get what you want to get in the end. Okay, so one distance that we looked at is L1 distance. And I would say there are the two main distances that people look at are either the KL divergence or this L1 distance. If you're an information theorist, or if you look at investments, you probably look at KL divergence. If you are a computer scientist or a data scientist, probably look at L1 distance. I think that's by and large correct. So the L1 distance, or essentially the total variation distance between two distribution P and Q, is just the sum of the absolute differences between them. So you just take the P probability of X and the Q probability, take the difference between them and sum them up. Okay, and that's clearly a value between 0 and 2. Okay, And it comes up in hypothesis testing and classification, as we're going to see right now. So why do people care about L1? So if they do hypothesis testing, then you have two known distributions, P and Q, they're known to you. And you, one of these two distributions selected at random, and you get a sample from this distribution. And from this sample, you want to decide which distribution was selected. So, for example, I have two coins. One of them I tell you is unbiased, Bernoulli half. The other one is Bernoulli 0.9. I get one sample, and I want to know, is it the unbiased coin or the biased coin? Okay. And you can show that your error probability is going to be 1/2 minus the L1 distance divided by 4. So it's directly related to the L1 distance. For example, if the two distributions are the same, then the L1 distance is 0. So you get your error probability is 1/2 because there's no difference between the two distributions. You will never be able to tell which distribution generated your sample. On the other hand, if your two distributions have disjoint supports, one of them takes values that are only negative, the other one only or the positive. One of them is all the values that you'll get will be less than 0, and the other one, all of them will more than 0. The L1 distance is going to be, in this case, when you get a sample, you'll be able to immediately tell which distribution generated the sample. The L1 distance is 2, and you get 1/2 minus 2/4, which is 0. Okay, so that's one reason you care about the L1 distance. And the other one is classification. So if P and Q now, same problem, but P and Q are not known, then what you want to do is you want to learn them from the training samples. And if you can estimate the two distribution P and Q to L1 distance delta, then your probability of error is going to be the hypothesis testing error plus this delta error in your estimate. So that's why in machine learning, it's probably like the most common distance that people look at. Okay. So in this, I'm going to skip a bunch of things, but in this paper with Sudeep Kamath and Dheeraj Pichapati and Tirtha Suresh, we showed that for L1 distance loss, the actual loss is what you get here, and so we also were able to get the right constant for the L1 distance. And one thing to remember here for the rest of the talk is that it clearly grows with K, with the alphabet size. So if you want to learn distribution over a larger alphabet, you'll have a larger loss. And it goes goes down with N. And in fact, it goes down like square root of K over N. The square root of the alphabet size divided by the number of samples. Okay? So that's just something to keep in mind. Okay? And we also did other distances, and in particular, this implies that the instantaneous error in KL error is at least K over N, and other things. Okay, cool. All right. So, and the measure is exactly the same as what we did before. Okay. So this works for alphabet of size, any alphabet size, but the number of samples goes to infinity. And a very natural question is what happens when you have larger alphabets? So, like, where do you live? Do you live in the US? Do you live in China? Do you live in, like in asymptotic world, or so on? So if you're a magician, then you'll be flipping a lot of coins. So alphabet is size 2, and you're doing something of many times, and N is very large. Okay. Or if you're giving homework, probably that's one thing you'll do. So I have alphabet of size 2, flipping coin, a whole bunch of numbers times, and I want to say something about the probability. But if you live anywhere else, not in this asymptotic regime, like if you try to do language processing, so then the number of words, as we said, is maybe 500,000, and you might think that if you're Google or OpenAI, then you have a lot of samples, but in fact, you try to estimate the distribution given a context, and given any context, even Google, even OpenAI, the number of times this context appears is very small. So you don't have as many samples for a given context. Or if you work with genomics or economy or ecology or epidemiology or advertising, your alphabet size, the number of elements that you deal with is very large. You don't have so many samples that you can imagine. I have arbitrarily more samples than the alphabet size. Okay, so so the challenge in all these applications is that K is either proportional or maybe even larger than the number of samples. Okay, Okay, and the question is what you do then. So the K loss, as we said, was K minus 1 over 2n. This is Brace and Sawyer. And as K goes to infinity, this loss will go to infinity. And if we look at L1 distance, then it's square root of K over n. And then as K will go to infinity, this will actually go to 2, which is very natural, right? If I even have 1 million samples, if I have a distribution over 2 million elements, I will not be able to even see most of them. So both distances will be large, okay? So all estimators will have high loss, and that makes them hard to evaluate, okay, and to compare. And in fact, it leads to poor estimators. So if you can even show that if you take an estimator that's based on this asymptotic regime when n goes to infinity, and you apply it to practical regimes, then it will give you a poor estimator, okay, which is opposite of those that are used in practice, okay. So what we need is we need a new measure, okay. Okay, so to do that, let's do a little bit of genealogy, okay. So here's a genie, and we can look at the KL divergence. Remember, it's the summation of P of X log P over Q. Okay, we can view it as summation P log 1 over Q minus summation P log 1 over P. That's how we started, right? That's the number of bits that we use minus the entropy. Okay, so in other words, it's the compression length of P according to our estimate Q minus the optimal compression length of P. So we can view the optimal compression length of P, which is the entropy, as the compression length of a genie, the genie that knew the distribution exactly. So if you had a genie that knew the distribution exactly, then the genie would need P log 1 over P, this summation, we need the entropy, but we need this P log 1 over Q. So we're comparing ourselves to the performance of a genie that knows the distribution exactly. When you look at it this way, then a very natural question to ask is, what if I look at a slightly weaker genie? Okay, so what we want to do is consider to a weaker genie, but still a genie, we want to find a genie that will be stronger than any human, any of us, but doesn't know exactly the distribution, but knows more than we do, okay? So, and what we want to do is we compare to this weaker genie, and because this weaker genie is still stronger than any human, we will be actually comparing ourselves to all humans. So we're going to say, okay, we can do it as well as any human being can perform still, okay? And what we'll do is we'll choose a genie that's essentially, hopefully you'll agree with me, is not restricted, okay? So we call this a natural genie. Here it is. You can see its hands are slightly tied, okay? So this genie knows the distribution P. It knows everything. It knows the actual distribution, but it's slightly restricted in the sense that if two symbols appear the same number of times, then it has to give them the same probability. Okay? So for example, if I look at the sequence BO bookkeeper, BOO, KK, EEPR, and I try to estimate the probabilities of every letter, then B and P and R appeared once. Even though it knows the probabilities, it knows them exactly, it has to give them the same probability. Okay? If we look at O and K, they both have appeared twice. It has to give them the same probability. It knows the probability, and it can use what it knows, but it has to give them the same probability. And then for E appeared 3 times, it can give whatever probability it wants. So because we're assuming that the sequence is IID, then this assumption that it gives the same probability to things appearing every number of times will hold for all reasonable estimators, all those that we'll design, and it's also very natural, and you can also show that using our measure, the min-max measure, it's optimal, because if I see two symbols, appear the same number of times, 2 symbols appeared 3 times, or in this case, O and K, both of them appear twice, I give O a higher probability, I'll be doing worse. Both it doesn't make sense, and also in our measure of min-max. Okay, so this is a very natural genie to use. And practically is no restriction. There's no other thing that anyone would do except give the same probability. Okay, so what we want to do is do a competitive estimation where we compare our performance to the performance of this genie. So the risk of an estimator Q for P is the estimator. So we have estimator Q for probability P is the expected KL divergence. That's just like we said before. And the risk of the best natural genie, which we call RP of the natural genie, is the minimum of the risk of all risks of all natural estimators. So we're choosing the Gini. That has to be natural, but we're choosing the one with the lowest risk, okay? The lowest expected extra number of bits. And the regret that we have to the best natural Gini, so our regret to the Gini of a distribution P is going to be the difference between our distance, our Q for the estimated Q, minus the best regret for the best risk of any Gini, okay? So it's a difference from the Gini's compression. You can look at as the difference from the Gini's compression length. And it's the mean runs, and we define then the min-max regret for n to be the minimum of all possible estimators that we can choose of the maximum of all possible underlying distributions that we don't have control over, of this difference between our loss and the Gini's loss. Okay, so we want to make sure that our loss is very close to the Gini loss under any underlying distribution. Okay, so it's the worst increase of a natural Gini that knows the underlying distribution P. So we know that if you look at the most all-powerful Gini that know the distribution and was not limited, then our loss is going to go to infinity. It's k over 2 log n, k over 2n, so k increases will go to infinity. So here we're doing something very natural, that we're just saying if the two things appear the same number of times, we have to give them the same probability, which is what everyone would do. So the question is, why do we even have a chance? How can we even fight? How do we have a chance of fighting with this Gini of performing about as well as the Gini? Okay, so notice that the natural Gini, if it sees the word bookkeeper, then it will have to give, so we can see what is the probability that it will give to the letter E. It's going to be some value, which is P, which is it knows P, so it can give this value. Now, and P is known, okay, so that's fine. Now, let's look at the letters O and the letter K. Both of them appear twice. It will have to give them the same probability. It knows the two probabilities. Maybe one is 0.1, the other one is 0.3. It has to give them the same probability. And after some thought, you can see that the best probability that will give is going to be the average between these two values. So the sum is going to be P plus the probability, probability of O plus probability of K instead of S and T. But each one gets the average. And what probability does it assign to B, P, and R? Each of them appeared once. They have to give them the same probability. It's going to be just the average of the three probabilities. You can show that that's what this Gini will do. Okay? So one natural question you might have is, what information does the Gini have in order to make these estimates? Okay? And because if we know what information it needs, then we can emulate the performance of the Gini. Okay, and when you look at this, what the Gini needs is the total probability of all the elements that appeared once, twice, and so on. So to find the probability, the probability of E appeared 3 times. There's only one symbol that appeared 3 times. It gives us the probability. Find the probability that it gives, for example, let's look at this, B, P, and R. Each of them appeared once. Then it needs to know the total probability of all the elements that appeared once, this total probability, and then we'll just divide by 3. And here it will look at total probability of all elements that appear twice, O and K, and just divide by 2, give each one a half. So in other words, and it also needs to know the probability of elements that appear 0 times. It needs to know that. Okay, so the question is, how many parameters does the Gini need to evaluate? Okay, so the number of parameters that it needs to evaluate, so given a sample size, we're looking at the largest number of non-zero parameters. And those that appeared, So look at number of elements that appeared twice, and I'm sorry. So we look at the largest number of non-zero parameters. This largest number you will have if you have one element appear once, one element appear twice, one element appear 3 times, and so on, up to one element appearing t times. So for example, if you look at a sequence here, so the Gini will need to know the probability of all the elements appeared once, all the elements appearing twice, probability of all elements appearing 3 times. We want to see what is the largest number of parameters it will need to know. It will be this number will be the largest if you have one element appeared once, one element appearing twice, one element appeared 3 times, and so on. Because then it will need to know the probability of all elements appeared once, twice, and so on. If you only had many elements appearing the same number of times, then for all of them, we will just need to know one parameter. So the worst for you is if you have one element appearing once, one element twice, and so on. And if we have n samples, then we know that if n is going to be, we have one element appearing once, and one element appear twice, and so on, the total number of samples you have is going to be 1 plus 2 plus 3 plus t, and that has to be at most n. So the number of elements, and then we also need the number of elements appearing 0 times. So therefore, t is going to be at most square root of 2n, right? Because this is the arithmetic sum. So t is at most square root of 2n, and then we need to know number of elements appearing 0 times. So the Gini needs to know square root of 2n plus 1 parameters. And that's good news for us, because with n parameters, we can estimate, we can learn square root of n parameters. Because as you remember, square root, the answer for estimating in general is square root of the alphabet size divided by the number of samples. So here the alphabet size is square root of n. You're trying to estimate square root of n parameters with n samples. You can actually learn. So what we can do is we can actually learn the Gini. But then to find the estimator, the actual estimator that does it, requires a little more work. And here we got a little bit help again from others, Good and Turing. So during World War II, Good and Turing, they tried to decipher the Enigma code. And to do that, they actually developed the world's first computer, but was obviously still a little slow. And so there was something that helped them, which is they captured the book of German passwords. So the Germans insisted that all the U-boat commanders, in this case, they choose the password from a book, a very large book, obviously. And so they had decrypted a few messages before, and from that they tried to guess the passwords, the pages that each U-boat commander would choose from. So maybe one would choose only from the right side of from the even pages or the odd pages or the beginning of the book and so on. And so from that, then they were trying to estimate the distribution of these pages. And this, of course, was immortalized in the imitation game that talks actually about this exact problem that they're trying to solve. So, okay, so the formula that they came up with is a little unique. They showed that if you want to estimate the probability of an element that appears t times, so what we're going to do is let phi of t be the number of symbols that appeared, that were observed t times. So their estimate was, the estimate that they give to an element that appears t times is going to be t plus 1 over n. T plus 1 over n is very close to the empirical frequency. If something was observed t times, you give it probability t over n, that's okay. But then they multiplied it by this unintuitive factor, which is the number of elements that appear t plus 1 times divided by the number of elements that appear t times. Okay? And so, and then in this paper, what we showed that if you take a variation of good Turing, in fact, we looked at 2 different variations, then your loss compared to the Gini, to the best Gini, is going to be the minimum between k, the alphabet size, square root of n, which is the number of, n is the number of sample, divided by n. So if you draw it as a graph, as a function of k, it's going to go first linearly in n, and then when k becomes n, a square root of n, then it's going to stay flat. Okay? So you notice that this in particular is less than or equal, always less than or equal to 1 over square root of n. And that means that you can learn as well as the Gini, regardless of the alphabet size. So the alphabet size doesn't matter anymore. You may not be able to learn as well as the Gini that knows the distribution, has loss 0, but compared to any realistic Gini, even one that knows the distribution but is restricted to this very natural assumption, then you lost extra losses that most 1 over square root of n. This notation here means that we're hiding, there's a log factor here that I'm not writing, but smaller factors. Okay? And here is a comparison. So, so here we have the min-max loss, which we know is k over 2n, and then the best the loss of the best genie is shown here in the red, and our loss is going to track the loss of the genie. Here, for example, if you take uniform distribution, if the distribution is uniform, then that's optimal for this genie because it just gives everything the same probability. It has loss 0, and we'll still track it, but we track it in all domains by at most 1 over square root of n. So there's the loss does not depend on the alphabet size. Okay, all right. So we perform almost as well as the genie, and therefore almost as well as any human might. Okay, and these are simulations, basically they show, so the red is the loss of the genie, and you can see different estimators that people use, and the green is our estimator. Okay, cool. All right, so to summarize, general distributions can be arbitrary, can be non-parametric, and we compare it to the natural genie, which is stronger than any human, and we can learn any distribution essentially as well as the genie, and the additional loss is 1 over square root of n, regardless of the alphabet size. Cool. So what do we learn about this new measure? It says that if your boss calls you and says, "Hey, your work is fired. Is terrible. You're fired," then you can tell him, "Hey, here is a proof that no one can do better. Like, yeah, I'm having a big loss, but even this genie will have essentially this big loss," and says, "Wow, that's really great. You're promoted." Okay, so changing the measure a little bit to making it competitive may help. Okay, Paul, how much time do I have?
You want an estimate, or
I want a loose upper bound.
It's 11:53.
Correct.
So is 10 minutes?
Yeah, we'll do our best. Okay, cool. Okay, so then we want to talk about structure, and the first thing that you'll ask is why. And the reason you ask is why is because I just told you can learn the distribution as well as the genie. There's nothing. Why would we even want to do better than that? 1 over square root of n is such a small difference. Then why do we even need to look at structure if we can learn any distribution as well as the genie? Okay, so there are a couple of reasons. The couple of reasons I said more or less, or maybe I should say not more or less, but more and less. Okay, so more is I want to give you an assumption where making structure assumptions will help you. More assumptions about the structure. So consider bivariate distributions. So you have a distribution over 2 values. And suppose that I told you that for some reason, this distribution has a structure like this. So all the pink values have the same probability, and all the gray values have another probability. This is not far-fetched. People make this assumption. If you have a group of people, then you have communities, and people within the same community, they have some probability of contacting each other, but between different communities, they have different probabilities. So in this case, if I know that the structure is of this form, if I can learn here, if I can learn the probabilities of a bunch of symbols, and I know that this structure exists, I will be able to tell the probability of elements in between, even though I've not seen them. So even though they appear 0 times, I'm not going to give them the same probability as other 0, because I know that they're in this group, and I will give them the same probability as other elements in this group. So the fact that I know there's structure helps me give probability which is different from what I would give just based on the empirical frequencies. Okay, so that's one assumption. Or the distribution is continuous, and maybe I can assume some continuity. Again, you'll give, even though you maybe not have seen some values in between, you're not going to give them 0 probability, you're going to give them probability which is close to the neighbors. So you do more than just looking at how many times things appear. And I wrote here, skip this for an interest of time. We might end up skipping almost all, or maybe all. Okay. Or you have high dimensional data. Again, there's some structure there that you can be used to get better estimate. So this is when assuming more structure might help you. There are cases where you also want to assume less structure. So for example, what we talked about so far was just IID distributions. But in reality, of course, distributions are non-IID, so there may be Markov distributions. So this assumes less structure, that the samples are not as structured as IID, but the distribution may be a little different. So there are many reasons. So we're not done. There's more work to do. Okay. Let me just go quickly over the results that we derived. So bivariate distributions they appear in many cases. So if, for example, if you look at buyers and products, so you have Amazon, you have a collection of buyers, you have a collection of products, and you want to estimate what's the probability that a buyer will buy, a user will buy a specific product, or viewers and movies, you want to estimate what's the probability that a user will be interested in a given movie. All these are bivariate distributions, okay? And in many applications, and the point here is that without assuming this a structure, we will not be able to learn, because here the number of samples is maybe every person. So if you look at Amazon, maybe they have, I don't know, tens of millions of customers or hundreds of millions, and they have millions of products. It's not the case that every user bought a million products. So the number of samples they have is not going to be proportional to the size of this matrix, which is k times m. Maybe every user bought like a few products, like a constant number of products, like 50, 10. So the question is, can we get estimate when the number of samples is proportional to just one dimension, not the product of the dimensions, okay? And again, this looks bad, but it gives us this opportunity to look at something better. So one assumption that people like to make is that the matrix has low rank. So the probabilities have a low rank. Viewed as symmetrics, they're low rank, and typically, so is linear relation, so it's low rank. So if it's low rank, then the number of parameters, if the rank is R, the number of parameters is going to be R times the maximum of the two dimensions. Okay? In other words, proportional to the maximum of two dimensions. That gives us hope, because we do have that. It's reasonable to assume that we have that many samples, that every user bought a few things, or every product was bought a few times. Okay? So previously, so people have looked at this. Just a second. So this is work with Ayush Jain. So we looked at all matrices of length less than or equal to R. And we looked at, again, the min max loss, and other people have looked at it, but the results that they got were suboptimal, okay, like the rank to the fourth and n of the 1/5. And what we showed is that the number of samples that you need, or your loss, is going to be at most square root of k times R over n. Notice that it has the same growth rate as before, because k times R is the number of parameters, n is the number of samples, square root of the ratio is the loss the best loss you can get, and we can show that you can achieve it up to a log factor. Okay? So, and furthermore, that this could be done using a polynomial time algorithm. So, and so this just hides this constant factors, and can be done this. So, polynomial time algorithm. So this shows us that actually you can learn such distributions. Okay. All right, and then the results for high-dimensional mixtures and so on that I'm going to skip a lot. I'm just trying to maybe give you a flavor of another type of question that you might ask. Yeah, so let's look at trying to learn the fruit, not interested in the whole distribution, but some maybe aspect of the distribution. Okay, so far we talked about learning a distribution. But in many applications, we're not interested in the distribution, but some function of the distribution. It's called distribution functional, and it maps the distribution to a number. There are many functionals that people look at. For example, you can look at the support size. If samples from a distribution, what is the size of the alphabet? How many different species are there? How many different variations of disease are there, and so on? Or you can or what's the vocabulary of a person, or what's the population of a city, and so on. Or you can look at the entropy. Okay, that's a function of the distribution. It comes up in many applications. Or the distance to uniformity. Comes up when you want to say whether a distribution is uniform and so on. So these are all functions of the distribution. If you're given the distribution, I can say what is the support size, what is the entropy, how far is it from uniform. Okay? And I'm going to skip the old definition, I think it's clear. And a natural way to estimate this value is to do it in 2 steps. Take the samples and then come up with an estimate for the distribution, okay? And then apply the functional to the estimate. And the rationale is that as the number of samples goes to infinity, then your estimate will go to the actual distribution, and then you can apply the functional to the estimate. It will be roughly the functional applied to the distribution itself. And the simplest estimate is empirical estimator. So, for example, if I get this sequence, and I try to estimate the entropy of the underlying distribution, then I'll say my estimate of the distribution is A appeared 4 times, so its probability is 0.4 out of 10. C appeared twice, 0.2, and B appeared 4 times, so its distribution is 4.4, 0.4, 0.2, and then I just estimate the entropy of this distribution. So this is a plug-and-play estimator. It's universal, and it's intuitive, many advantages, and it's also the best known and most used functional estimator, but it turns out not to be optimal. So people have figured out about, I would say, maybe 10 years ago that these estimators are not optimal. And they came up with estimators for very different functionals, for entropy, for support size, and so on. And we came up with an estimator that works universally. So it works for all symmetric functional. So symmetric functional is most functionals that you will look at are symmetric, so invariant under label permutation. So for example, support size. It doesn't matter if you change the labels, the support size is the same. Entropy, again, invariant under labeling, relabeling of the values, distance to uniformity, and so on. So the entropy of 0.6, 0.2, 0.2 is equal to the entropy of 0.2, 0.6, 0.2. And the question is, can we find one efficient estimator that will work for all symmetric functionals? And one thing to observe is that because we're looking at symmetric functionals, they're determined just by the probability multiset. So here, we don't care the order, we just care that the probabilities are 0.6, 0.2, 0.2. And because we only care about the set of probabilities, or multi-set of probabilities, then what we showed was, approach that we took was to just try to find the distribution that will maximize the set of elements that we see. So for example, if we see heads, tails, heads, we just say we have one element appearing once and one element appearing twice. If we see bananas, we don't care about the exact sequence bananas. We just say that we have 2 elements that appeared once, that's B and S, and we have one element appear twice, that's N, and one element appearing 3 times. So what we are trying to do is we've tried to find the distribution that will maximize the probability of this profile that we see. Okay, so it's efficient statistic, and that's what we try to find, the distribution. So empirical estimator try to find the distribution that maximizes the probability of the sequence. Yeah, and so for example, if you see heads, heads, tails, it will tell you that the probability of heads is 2/3, 1/3, and therefore the set is 2/3, 1/3. Whereas we will ask, what is the distribution that will maximize the probability that if you take 3 samples, one element appears twice and one element appears once. That's the profile maximum likelihood. So we say one element appeared once, one element appeared twice. There's a little bit of math that needs to be done, and that turns out to be 1/2, 1/2. That will maximize that probability. And when you do that, then you can, this is the definition of error, you can actually show that for any additive functionals, like support size, entropy, distance to uniformity, and so on, then if you take this approach, your loss will be, your distance from the best will be the best that you can have, plus alpha over n to some constant, like 1 alpha over n to the 1/4, regardless of the underlying distribution, regardless of anything. Okay, so so it works for all of these, and these are some examples that shows how well it works, and so on. So let me then just stop here. So skipping, as you can see, a whole bunch of stuff. And so basically, just maybe resume here. So we started by talking about compression. We saw how we could use it for estimation and estimate as well as the Gini. And then we talked about structure, estimating like low rank distributions, estimating functionals. This has to do with estimating when there are errors, robust estimation, and so on. And we learned that the information theoretic equivalent of Archimedes, sometimes it's good to come up with a good measure, helps you get good results, and to also see what other people have done also helps you get good results, and that bad can be often turned into good. And so this is the story, and I want to end by just thanking my collaborator, my students and postdocs over the years that have been amazing and have essentially driven all these results. So thank you. Excellent question. So Lempel-Ziv is a specific way of performing universal compression. It has a lot of advantages and maybe one small disadvantage in this context. The biggest advantage is what I spoke now is about compressing IID distributions, and Lempel-Ziv applies to non-IID distributions as well. So I'm talking about like flipping a coin, it's always the same distribution, but you might think it's a Markov chain or some more complex distribution. So that Lempel-Ziv applies to more complicated distribution. So that's a huge strength compared to what I described. In terms of achieving the best performance for a given distribution, they may not be, they're very good. You can show that they perform really well, but maybe not the absolute best that you can for a specific.
But you had that ratio that showed that the average was almost as good as the best.
So,
and therefore, that's why it works so well.
Correct. So what I spoke here is about IID distribution. You take samples from a distribution. So imagine you have a distribution, take samples. Then it's very natural to say that it's IID distribution. I catch a butterfly, I catch another butterfly, and so on. Or I take a user, another user, and so on. It's IID, the same distribution. And then the results that I spoke about here apply. If you look at Markov, for example, we've also worked on Markov distribution, which I have not described. If you work on Markov distribution, then it's not going to be k minus 1 over 2. It's going to be a different answer that depends on the entropy. You could still show that you can learn it. You can learn it universally, even if it's a Markov chain, but the results are going to be a little different because the number of parameters is going to be different. Right. Yeah. So there is a type of results that says universal for all sequences. We are not looking at these. So we're looking at learning, if I understand you correctly, you want to be almost optimal for any sequence. That limits what you can prove. So you can prove it in certain contexts, like you will not be able to prove it in this context. For example, if your alphabet is large, you will not be able to prove it for every sequence because you may see elements that you have not seen before, and you lose on each of them. So you will not be able to get the universal for each sequence. But we think that it's a good compromise. Right? We want to be able to get results for anything under the assumption that there is some distribution, not to be the best, essentially the best for every sequence. Thanks.
Alon has given lots of nice posters at the ITA workshop, so we're going to give him something in return, a flyer.
Thanks. Thanks, Paul.
Okay, I did want to mention just one more thing. Typically at the Shannon Memorial Lecture, we announce the Shannon Graduate Fellowship recipient. We had a few recipients during COVID, and so they're listed here at the bottom from 2020 and 2021. This is the list of all of the recipients over time. And then we had an award last year. Unfortunately, we did not have a Shannon Memorial Lecture last year because of some scheduling difficulties. But I wanted to at least acknowledge that Spencer Conjero, who was nominated by Ken Ziegler, won the award. And this year, you're probably wondering who the winner is. And I'm wondering too, because we haven't decided yet. So you'll have to come to the lecture next year to find out who the 2023 award winner is. Thank you very much.
So was it